Hi, today we're going to do proving triangle congruence by ASA and AAS congruence theorems. So you already learned three very important theorems that are used for triangle congruence, and we'll look at two more that will be absolutely essential in geometry and obviously chapter 4 as well. First, what is the ASA congruence postulate? First, ASA congruence postulate is when a side angle, and angle are congruent to each other, and note that this is a postulate. So remember SSS, ASA, and SAS are postulates, but the HL theorem and the AAS congruence theorem are theorems. So that's a key difference here you have to know. But here ASA is when there's an angle, side, and angle. So no, here like the SAS, the side in this case must be an included side. And the AAS congruence theorem is when the angle side is congruent, and it has to be in a manner like where it's an angle side. It can't be like a side angle or angle side or like in another way. And it must always be angle side in this specific like order as shown here below. I think it's pretty self-explanatory, but remember this is really important. This is absolutely essential in chapter 4 and in proving congruence for triangle as a whole. But next, let's look at like proving congruence here. Let's look at number 4, for example. This is a side, and an angle. There's no thing like a SSA or ASS congruence theorem or postulate, but there is an AAS. So in this case, this would not be congruent. But if you look at number 5, because this is angle, side, angle, then this is the ASA postulate. So obviously this is a these are congruent triangles. So let's look at 13 quickly. where is it? AED and BDC are congruent by ASA. So how do we know that? Obviously, AED here is they both have an equal angle, which is seen here by a right triangle. So we already have one angle here. But looking at the side itself, we know that these sides are equal. So we have another side. And angle wise, note that the relationship between these angles is a parallel. So these two angles will also be congruent by the corresponding angles postulate, right? So that would make these two triangles congruent. And I think that's really it for here. But let's look at how we actually use congruent triangles itself. Obviously, triangles, there's a variety of shapes that are triangles in real life. This is even seen here, like a kite has some sort of triangular shape, or just for a measurement of certain things. So here are just how triangles generally work. I think this is pretty self-explanatory. Let's look at number 8 here. So tell which triangles key can show are congruent in order to prove the statement. So you're trying to show these two triangles are like congruent, let's say. I think we already know that these two angles are congruent. Same here, and another side. We know two angles and a side, so this would be the AAS theorem that will be used, for example. If we do a really quick, let's see, it's a really quick proof as like a final. Where is it? Okay, let's look at number 39. So we're given that so we are given BA is congruent to BC, D plus E are, okay, this is a bad notation, D and E are midpoints. Angle A is congruent to angle C, and angle DF, side DF is congruent to EF, is what we're given. And we have to prove that FG and FH are congruent, so that would be our goal. Okay, so to do this, what would be best is first to prove some triangle congruence, right? Because we're already given these angles, it would be best to try and prove that DH A and EG C are congruent. But obviously, first we know that these angles are congruent, so we already have an angle here. But what you have to know is we can't have ASS because that's not a simply put theorem. So I think what we need to do here is use first, because we know angle, side, side, and here is another side, side. We need to know either one more angle or one more side. And the more logical approach here would be to find an angle. And the way we would do this is because we know that these two angles are congruent by the vertical angles. We can also imply that that is the same for these two angles, right? And because of the alternate interior angles, we can also imply that these two angles and these two angles are also congruent to each other. So I think simply with just parallel lines, we can solve this proof. And lastly, let's look at using isosceles and equilateral triangles, and this will be the last thing for here. But obviously, an isosceles triangle is a side that is a triangle that has two or more equal sides and angles. And we can use two main theorems in this case. First, the base angles theorem, which is when if two angles, let's say B and C are congruent, then the sides are opposite to them are congruent. So it would be like this, right? And the converse of the base angles theorem is basically what a converse is the opposite. So if here is the angles, which leads to congruency for these sides. Next are some corollaries. Now, corollaries are not like the most common nor important, but note that you still have to know them here. But corollaries are kind of something that like derives from a theorem. So obviously, in this case, this corollary derives from the base angles theorem, right? So if a triangle is equilateral, then they're equal angular. You might think that this is pretty obvious, but when you're trying to show this in a proof, you need to write that it's that you're using the corollary to base angles theorem. The corollary to the converse of base angles theorem is just the opposite. Let's look at a simple algebra. Find the value of x. Here we know that these two angles are equal, so x would be 8. I think this is pretty simple algebra that really derives from algebra 1. It should not really be a challenge for you guys. I think that's it. So great job today and keep the good work. Bye.